September 19, 1944, northern France. A heavy morning mist lay across the low farmland near the village of Ariol, blurring hedgerows and swallowing distant shapes. Visibility was poor, the kind of weather that turned armored patrols into exercises in nerve inside a U.S. Army Sherman tank. First Lieutenant Merwin Men of the 37th Tank Battalion braced himself against the edge of the turret hatch while his gunner searched the grey haze through a periscope. Inch by inch, the crew knew what might be waiting beyond the fog. German Panther tanks had been reported in the area, machines that had already earned a grim reputation among Allied tankers. Their sharply angled armor and powerful guns had repeatedly demonstrated an unsettling ability to absorb American fire and respond with lethal precision. Men and his crew believed they were entering yet another engagement where survival depended on speed, positioning, and luck. What they did not realize was that their Sherman carried something rare and quietly revolutionary. Stored among the standard shells were 6 experimental rounds unlike anything most American tank crews had ever fired. These were Men-93 high-velocity armor-piercing rounds, each built around a dense tungsten carbide penetrator. In the right conditions, they could turn an ordinary Sherman, long considered inferior in tank versus tank combat, into a weapon capable of punching through armor once thought untouchable. The effect of this ammunition would extend far beyond its physical damage. It would unsettle German crews, overturn long-held assumptions about American limitations, and force a painful re-evaluation of the Panther's supposed frontal invulnerability. The origins of this shift in battlefield reality, however, lay far from France. A problem identified too late. Months earlier, in the United States, metallurgists, ordnance specialists, and ballistic engineers were racing against time. Their task was urgent: solve a flaw in American armored warfare doctrine that had become impossible to ignore. By early 1944, U.S. Army planners were confronting a problem they had not adequately anticipated. The M4 Sherman, reliable, mobile, and easy to produce, formed the backbone of American armored divisions. But in combat, it was increasingly encountering German tanks it could not reliably defeat head-on. At the center of the issue stood the Panther. Designed as Germany's response to the Soviet T-34, the Panther combined several advances into a single platform. Its long-barreled 75mm high-velocity gun delivered excellent accuracy and penetration at range. More critically, its frontal glacis armor measured 80mm thick and was angled at approximately 55 degrees. This slope dramatically increased its effective resistance, equivalent to roughly 140mm of vertical armor, far beyond what most American tank guns could handle. U.S. intelligence assessments before the Normandy landings had severely underestimated both how many Panthers would appear in Western Europe and how widely they would be deployed. Planners expected them to be rare. Reality proved otherwise. Normandy's harsh reality. When Allied forces came ashore in June 1944, the scale of the miscalculation became clear. Panthers were not occasional threats, they were a core component of German armored strength. By that point, roughly 38% of German tanks in the Normandy theater were Panthers, numbering in the hundreds. Many were crewed by soldiers with limited experience, but their lack of training was offset by armor protection that rendered frontal engagements lopsided. The standard Sherman in Normandy carried the 75mm M3 gun, a weapon effective against earlier German designs but wholly inadequate against the Panther's frontal plate. At any realistic combat distance, American rounds simply deflected off the sloped armor. The Panther, meanwhile, could destroy a Sherman from distances exceeding 2 kilometers, often before the American crew even realized they had been targeted. The limits of the 76mm upgrade. The introduction of the 76mm Moan gun was intended to correct this imbalance. Beginning in July 1944, Shermans armed with the more powerful weapons started reaching frontline units. On paper, the upgrade looked promising. Firing standard Mi-62 armor-piercing capped ammunition, the 76mm of gun could penetrate approximately 109mm when striking at a perpendicular angle. This made it effective against Panzer IV tanks and many German assault guns. Against the Panther, however, the improvement fell short. The Panther's sloped frontal armor still resisted penetration. In theory, the 76mm could punch through the gun mantlet, but only under extremely favorable conditions, usually at distances under 100 meters. At such close range, the Panther's superior firepower and optics made the engagement extremely dangerous, often fatal. The gun itself was not the true limitation. The ammunition was. A decision deferred. Ironically, the 76mm Sherman had been available well before the Normandy invasion. Production of M4A-owned Shermans mounting the 76mm monogun began in January 1944. By April 10th, approximately 130 of these tanks had arrived in Britain, ready for deployment ahead of D-Day. Yet they were not committed to the initial landings. American commanders hesitated for several reasons. Tank crews had limited time to train on the new weapon system. Supplying both 75mm and 76mm ammunition complicated already strained logistics. Most importantly, senior officers believed the existing 75mm gun would be sufficient for the anticipated German opposition. That assumption proved disastrously wrong. It was only after months of costly encounters when the Panther's dominance became undeniable. That attention turned to alternative solutions. Among them was a small batch of specialized ammunition, quietly issued, rarely discussed, and capable of changing the battlefield equation when used correctly. Those 6 tungsten-cored rounds carried by men's Sherman were part of that solution. And they represented a turning point born not of new tanks but of a radical rethink of what a single shell could do. By the first days of July 1944, the optimism that had accompanied the Allied landings in Normandy was rapidly evaporating. Reports arriving from the front lines told a consistent and troubling story. American tank units were encountering German armor that their weapons simply could not handle. On July 2, these concerns reached the highest levels of command. Field officers openly questioned the effectiveness of the Sherman's 75mm gun when facing Panthers, and the issue was formally raised with General Dwight D. Eisenhower. Eisenhower's reaction, preserved in several post-war accounts, reflected a deep sense of disbelief mixed with anger. According to those present, he reacted sharply upon learning that the newer 76mm gun was also failing to deliver decisive results. He had been led to believe by Ordnance Department assurances that the weapon would be more than capable of dealing with any German tank encountered in France. The realization that this promise had not been fulfilled sparked visible frustration, and his remarks reportedly escalated into blunt, unfiltered criticism of the planners who had guaranteed the gun's performance. Just 10 days later, on July 12, 1944, a formal evaluation board convened to assess the situation. Its conclusions merely confirmed what American tank crews had already learned under fire: standard U.S. tank armament, even with the 76mm upgrade, was incapable of reliably penetrating the frontal armor of the Panther. This official acknowledgement removed any lingering doubt. The problem was systemic, not anecdotal. In response, General Omar Bradley acted quickly. He ordered all available 76mm armed Shermans still in Britain to be shipped to the Normandy front without delay. The first opportunity to deploy these tanks on a large scale came during Operation Cobra. On July 25, 1944, a force of 102 M4A-owned Shermans equipped with the 76mm gun entered combat for the first time. Expectations were cautiously hopeful, but the battlefield results were sobering. While the 76mm gun offered modest improvements over its predecessor, it still fell short against the Panther's frontal protection at normal combat distances. American crews adapted as best they could. They learned that survival depended on maneuver-seeking side or rear shots or, in desperate situations, attempting to strike the Panther's gun mantlet at close range. Neither approach was tactically sound when facing an enemy tank capable of destroying a Sherman from distances exceeding 2 kilometers. The real breakthrough would not come from tactics alone, but from advances in materials science and ballistic design. By mid-1944, engineers within the U.S. Ordnance Department had finalized a new type of ammunition known initially as the T4, later standardized as the Men-T3 high-velocity armor-piercing round. HVAP ammunition marked a radical departure from traditional armor-piercing concepts. Instead of relying on mass alone, the new projectile used a dense tungsten carbide core among the hardest substances available at the time, encased in a lightweight aluminum alloy body and capped with a ballistic windshield. This configuration allowed the round to concentrate enormous kinetic energy into a small penetrator while significantly increasing velocity. The performance gains were dramatic. Fired from the 76mm gun, the Mi-93 achieved a muzzle velocity of approximately 1,036 meters per second, compared to roughly 792 meters per second for the standard Mi-2 round. This increase of over 240 meters per second translated directly into superior penetration. At a distance of 1,000 yards, about 914 meters, the HVAP projectile was capable of defeating around 160 millimeters of armor at a 10-degree angle. According to War Department test data, this level of performance was sufficient to penetrate the Panther's gun mantlet. Early Panther OSFD&A variants featured a curved cast steel mantlet approximately 100 millimeters thick, while later OSFF G models increased this to around 120 millimeters. With HVAP ammunition, the mantlet, once an impractical target, became vulnerable at meaningful combat ranges. For Sherman crews, this fundamentally changed the engagement equation, offering a realistic chance of victory without relying solely on flanking maneuvers or sheer luck. Yet technical success introduced a new problem: supply. The effectiveness of HVAP ammunition depended entirely on tungsten carbide, a material that was both rare and strategically vital. Before the war, China accounted for roughly 36% of global tungsten production, making it the primary source for Allied imports. Tungsten was in constant demand across multiple industries, including machine tool manufacturing, armor plate processing, and armor-piercing ammunition for various calibers. The scale of consumption was significant. Each 76mm HVAP round required approximately 0.88 kilograms of tungsten carbide. A single Sherman carrying 6 such rounds represented nearly 5 kilograms of tungsten, an enormous cost in strategic material. In 1944, China produced an estimated 10,000 metric tons of tungsten concentrates, but this output had to support the entire Allied war economy, not just tank ammunition. The United States attempted to offset this dependence with domestic mining operations in Colorado, Nevada, and California. However, these deposits were limited, and total supply remained constrained. Germany's situation was even more dire. As the war turned against the Reich, Swedish tungsten imports declined sharply, and domestic production was insufficient to compensate. By 1945, German industry prioritized tungsten almost exclusively for machine tools critical to aircraft engine manufacturing, leaving frontline Panther crews equipped largely with conventional ammunition. Although American engineers had begun experimenting with HVAP designs as early as the spring of 1942, mass production lagged far behind development. It was not until the harsh lessons of Normandy made the Panther threat undeniable that large-scale manufacturing finally gained momentum. In July 1944, production of 3-inch HVAP rounds for tank destroyers reached approximately 1,000 units. The following month saw a similar figure for the 76mm version. September added another modest batch, but meaningful output remained elusive. Only by November 1944 did monthly production climb to around 5,000 rounds for the 76mm gun. By January 1945, output reached approximately 7,000 rounds per month. By then, HVAP ammunition had proven its value beyond doubt. But its late arrival meant that many Sherman crews in Normandy had already faced the Panther threat without the one tool that could have decisively leveled the battlefield. By the early months of 1945, American industry had managed to manufacture roughly 33,000 rounds of 76mm high-velocity armor-piercing HVAP ammunition. This figure reflected a substantial logistical and industrial commitment, yet it fell dramatically short of operational demand. On the European battlefield, scarcity defined reality. As late as February 1945, a typical 76mm armed Sherman tank carried no more than 5 HVAP rounds in total. Those 5 shells were expected to counter an enemy that had largely standardized on the Panther tank within its Panzer divisions. When viewed at the unit level, the imbalance became stark. A standard American Sherman company fielding 17 tanks possessed only 85 HVAP rounds altogether, while opposing German formations could deploy 30 or more Panthers, each protected by thick frontal armor and armed with a long-barreled high-velocity gun. Although the first shipments of HVAP ammunition reached Europe as early as August 1944, their introduction coincided with a far more immediate set of tactical challenges. The fighting in Normandy forced American armored units into terrain dominated by hedgerows, narrow lanes, and limited sightlines. These conditions neutralized numerical advantages and played directly into German strengths. Panther crews learned to exploit the environment, setting up ambushes where Shermans advanced unknowingly into prepared killing zones. German tank doctrine emphasized first-shot lethality. Panthers were often dug into hull-down positions, exposing only their thickly armored turrets while concealing the more vulnerable hull. From these concealed locations, German gunners waited patiently, allowing American columns to close the distance before opening fire at ranges where return shots from Shermans were unlikely to penetrate. The psychological toll on American crews was profound. The Sherman gained an infamous nickname, the Ronson, a reference to the cigarette lighter slogan claiming it lights every time. While post-war analysis later demonstrated that this reputation overstated the vehicle's actual vulnerability, perception mattered more than statistics in combat. Fear altered decision-making. Tank commanders who identified Panthers frequently opted to disengage and call for artillery barrages or airstrikes instead of fighting directly, surrendering initiative to an opponent who could, under the right conditions, be defeated. HVAP ammunition had the potential to shift this balance, but its impact was blunted by limited availability and insufficient crew training. Many tankers were uncertain when, where, and how to employ the rounds most effectively. As a result, the ammunition's early battlefield influence remained muted. The first meaningful large-scale test of HVAP did not occur in the cramped terrain of Normandy, but rather in the open rolling countryside of Lorraine. By September 1944, Lieutenant General George S. Patton's Third Army had pushed deep into France, advancing at a pace that strained supply lines to the brink. Among Patton's spearhead formations was the 4th Armored Division, a highly experienced unit that drove aggressively eastward. This advance culminated in the seizure of a bridgehead across the Moselle River near Aricourt, a move that alarmed German command. Should Patton's armored columns reach the Rhine, the western defenses of Germany's industrial core would be dangerously exposed. In response, German leadership ordered General Hasso von Manteuffel's 5th Panzer Army to counterattack. The mission was clear: eliminate the American bridgehead and halt Patton's momentum. To accomplish this, the Germans assembled 2 newly raised formations, the 111th and 113th Panzer Brigades, equipped largely with factory-fresh Panther tanks. On paper, the Germans appeared overwhelmingly superior. Combined, the 2 brigades fielded around 150 armored vehicles, while Combat Command A of the 4th Armored Division could muster approximately 50 Sherman tanks. The 113th Panzer Brigade alone entered the operation with nearly 90 tanks and assault guns, including 42 Panthers and a similar number of Panzer IVs. German planners assumed technological superiority would compensate for American strengths in logistics, coordination, and air support. They misjudged the situation entirely. The fighting that followed, known as the Battle of Aricourt, spanning September 18 to 29, 1944, became the largest armored clash involving U.S. forces prior to the Battle of the Bulge. More importantly, it demonstrated that American armored units, when properly trained and coordinated, could defeat heavier German tanks through tactical discipline, combined arms integration, and selective use of specialized ammunition. The morning of September 19 opened under dense fog that clung to the low hills surrounding Aracourt. Visibility was severely limited, crippling German reconnaissance efforts. The Panzer brigades, lacking adequate scouting elements, advanced blindly into terrain already mapped, occupied, and prepared by American defenders. Shortly after 8 a.m., elements of the 113th Panzer Brigade pushed through American outposts to the east and south of the town. The German tanks, brand new Panthers, crewed largely by inexperienced personnel, advanced in column formation, a critical tactical mistake. Veteran American tankers immediately recognized the opportunity. Captain Kenneth R. Lamison, commanding C Company of the 37th Tank Battalion, had positioned his Shermans along likely avenues of approach. His crews had been briefed carefully on the limited HVAP ammunition carried aboard 6 rounds per tank. These rounds were not to be wasted. They were to be reserved for close-range shots against Panther turrets or mantlets where penetration was most likely. Ironically, the same fog that blinded German scouts now concealed American firing positions. A section of Lamison's tanks lay in wait south of Aracourt when the silhouette of a Panther suddenly emerged from the mist at a distance of roughly 75 meters. At such range, the Panther's long-range firepower offered no advantage. The American gunner fired immediately. The HVAP round left the barrel at over 1,000 meters per second, striking the Panther's gun mantlet. The tungsten-cored projectile punched through the curbed steel and ignited ammunition stored beneath the breech. The resulting explosion tore through the interior, lifting the turret slightly as the tank erupted in flame. Within moments, 2 additional Panthers rolled into view. Both were destroyed just as quickly, their crews unable to react before being hit. In the span of seconds, 3 German tanks were lost without a single effective return shot. The remaining German vehicles reversed course. Crews were stunned. What they had believed to be inferior American tanks had annihilated Panthers at point-blank range. The psychological shock rippled through the attacking force, marking a turning point not only in the engagement, but in the evolving understanding of armored warfare on the Western Front. Throughout the morning hours of September 19, fighting flared almost simultaneously across the Aracourt sector. Dense fog blanketed the battlefield, shaping the nature of the engagements from the very beginning. American armored units took full advantage of the limited visibility, maneuvering their tanks into firing positions where they could engage German Panthers at distances favorable to their newly issued high-velocity armor-piercing HVAP ammunition. Under these conditions, technical advantages that normally favored German armor were sharply reduced. German tactical execution during these advances proved deeply flawed. Panther units moved forward in narrow columns, often without adequate scouting or coordination. This formation repeatedly forced the tanks to expose their vulnerable side armor, creating ideal opportunities for American flanking fire. Rather than engaging from prepared positions, German crews advanced into ambushes shaped by terrain, fog, and American coordination. Near the Aracourt command post, a particularly destructive encounter unfolded. A platoon of mighty Hellcat tank destroyers, armed with 76mm guns and supplied with HVAP rounds, clashed with advancing German armor at extremely short distances. The Hellcat's speed and agility allowed them to reposition rapidly in the fog, striking Panthers before German crews could effectively respond. In these close-range engagements, the lightly armored but fast American vehicles proved lethally effective. As midday approached, atmospheric conditions shifted. The fog gradually lifted, restoring visibility across the battlefield. This change immediately benefited American forces, as forward artillery observers were now able to establish clear communication with defensive tank units. Artillery fire could be called in with precision, further disrupting German movement and assembly areas. Shortly thereafter, air support arrived. P-47 Thunderbolt fighter bombers from the 405th Fighter Group appeared overhead, exploiting breaks in the cloud cover to dive on German formations. Rockets and heavy machine gun fire tore into exposed armored vehicles, compounding the pressure already applied by ground forces. With artillery, armor, and air power now operating in concert, the contrast between the two sides' approaches became unmistakable. Individually, the Panther remained an impressive weapon. Its armor protection and firepower surpassed that of most American tanks when considered purely on technical specifications. However, American doctrine did not rely on individual platforms operating in isolation. Instead, U.S. forces consistently integrated tanks, infantry, artillery, tank destroyers, and aircraft into a unified system. German units at Arayort advanced without sufficient artillery preparation, lacked effective air cover, and frequently failed to deploy infantry support to neutralize American defensive positions. This imbalance in coordination proved decisive. German armor encountered layered defenses designed to exploit every vulnerability. Panthers were engaged, damaged, and destroyed incrementally rather than in decisive armored duels. Their technical advantages were rendered irrelevant by the environment in which they were forced to fight. The introduction of HVAP ammunition did not suddenly transform Sherman tanks into equals of the Panther in design or armor thickness. Warfare, however, is not governed by blueprints alone. Tanks are destroyed by trained crews who recognize weaknesses and exploit fleeting opportunities. The Panther's gun mantlet, essential for allowing elevation and traverse of its main armament, represented one such vulnerability. Additional weak points included the seam between turret and hull, the thinner side armor, and the exposed engine deck. With HVAP rounds, American crews could now engage these targets effectively at ranges that had previously meant near-certain destruction. Perhaps more damaging than the physical losses was the psychological shock inflicted on German crews. Panther commanders had been trained under the assumption that their tanks were effectively immune to frontal penetration by American weapons. Intelligence briefings emphasized the limitations of Sherman firepower, reinforcing the belief that maintaining a frontal aspect guaranteed safety. That belief collapsed under fire. The first crews to witness American rounds punching through mantlets and igniting internal ammunition learned that the battlefield reality had changed. Survivors carried this knowledge back to their units, and rumors spread rapidly. By the afternoon of September 19, German commanders were reporting to higher headquarters that American Shermans were employing unfamiliar, more powerful ammunition. These reports lacked clarity. Some officers speculated that American units had secretly deployed tank destroyers armed with 90mm guns. Others suggested British 17-pounder Firefly tanks had been attached to US formations. The actual explanation that American industry had fielded specialized ammunition capable of eroding the Panther's armor advantage was far more unsettling. It implied a level of industrial responsiveness that German planners could not easily match. Combat continued through September 22, by which time the main German offensive efforts had ground to a halt. In the fighting, American forces destroyed or disabled approximately 86 German tanks and assault guns. Their own losses amounted to 25 Sherman tanks and 7 tank destroyers. Despite facing technically superior vehicles, American units achieved a lopsided exchange ratio in their favor. The Battle of Arayort marked more than a battlefield success. It represented a turning point in perception. American tank crews gained confidence that they could defeat Panthers without relying exclusively on specialized destroyers or overwhelming airstrikes. German crews, in contrast, lost the psychological assurance of presumed invulnerability. From the German perspective, Arayort became a case study in confusion and recrimination. The 113th Panzer Brigade entered combat with roughly 90 tanks and assault guns. By September 29, fewer than 20 vehicles remained operational. After-action reports struggled to reconcile this outcome with the Panther's undeniable paper superiority. Training and experience provided part of the answer. Many Panzer Brigade crews had received only minimal instruction, sometimes mere weeks, before being committed to combat. American crews of the 4th Armored Division were veterans, hardened by months of fighting across France. They understood combined arms doctrine, terrain exploitation, and the realities of modern armored warfare. Yet training alone could not account for the nature of the losses, especially penetrations that should have been impossible using standard American ammunition. German intelligence officers inspecting wrecked Panthers noted entry holes that were smaller than expected. The evidence suggested the use of sub-caliber projectiles. The mystery was resolved when unexploded rounds recovered near disabled vehicles were examined. These rounds revealed tungsten-cored construction. The Americans had deployed HVAP ammunition. The strategic implications were significant. Germany itself had developed similar technology in the form of Panzer Granit 40, which relied on tungsten to enhance penetration. At Aricourt, however, it was American industry, not German, that had successfully translated such innovation into battlefield reality. By the final months of 1944, Germany's access to tungsten had become severely constrained. What little remained was increasingly diverted toward essential industrial purposes, especially the manufacture of precision machine tools rather than armor-piercing ammunition. This growing scarcity stood in stark contrast to the situation faced by the United States. When American forces were able to deploy specialized high-velocity armor-piercing rounds containing tungsten cores in quantities sufficient to supply frontline armored formations, it revealed a level of industrial depth and resource availability that Germany could no longer rival. American armored forces already benefited from numerical superiority and a logistics system capable of sustaining prolonged operations across vast distances. The introduction of HVAP ammunition added another layer to this advantage. These rounds did not render German armor obsolete, but they significantly reduced the margin of safety that German engineers had carefully built into vehicles like the Panther. Armor protection that once seemed nearly invulnerable under many battlefield conditions could now be compromised in specific, favorable circumstances. The significance of HVAP ammunition extended well beyond its immediate battlefield effects during engagements such as those around Aricourt. As reports circulated through American armored units that Panthers could, under the right conditions, be penetrated by this new ammunition, a noticeable shift occurred in crew behavior and mindset. During the difficult fighting in Normandy, many tank crews had developed a deep caution, sometimes bordering on paralysis, when confronting German heavy armor. That hesitation began to fade. American crews did not suddenly underestimate the Panther's firepower or armor, but they no longer viewed encounters with German tanks as hopeless. This psychological transformation proved to be a force multiplier. Confidence altered behavior, crews became more assertive, maneuvered to gain positional advantages, and accepted calculated risks that previously might have seemed too dangerous. In armored warfare, morale and perception often mattered as much as technical specifications. Even crews that never personally fired an HVAP round benefited from its existence. Simply knowing that such ammunition was available somewhere within the supply chain and might be issued when the situation became critical helped restore initiative. In this sense, HVAP served not only as a physical weapon, but also as a psychological one. However, the limited availability of tungsten meant that HVAP ammunition remained scarce throughout its service life. Commanders at multiple levels were forced to make difficult decisions regarding allocation. Tank destroyer units, whose primary missions centered on defeating enemy armor, were often given priority. Sherman tanks, which had to balance anti-armor duties with infantry support, frequently received fewer rounds despite encountering German tanks on a regular basis. This distribution system, managed across army, corps, division, and battalion levels, was far from efficient. Some formations found themselves holding more HVAP ammunition than they could readily employ, while others expended their allotment within days and were unable to secure replacements despite urgent requests. These disparities created tension between operational necessity and logistical reality. The problem became especially acute during the German counteroffensive in the Ardennes in December 1944. The surprise attack placed enormous pressure on American armored units operating in difficult winter terrain. German forces committed large numbers of Panthers and Tigers, exploiting conditions that favored defensive fighting and temporarily neutralized Allied air power due to persistent bad weather. In these circumstances, HVAP ammunition became a critical asset. Sherman crews relied heavily on their limited stocks to counter German heavy armor. Yet the intensity of the fighting quickly exhausted available supplies. In many cases, units ran out of HVAP entirely within days. Requests for resupply often went unanswered as supply routes were disrupted by snow, damaged infrastructure, and advancing German forces. Despite these challenges, American units demonstrated that tactical proficiency and combined arms coordination could offset technical disadvantages. Tank crews worked closely with infantry, using bazooka teams to ambush German tanks at close range. Shermans provided suppressive fire while infantry maneuvered into position. Artillery observers played a vital role, calling in precisely timed barrages that damaged optics, destroyed tracks, and inflicted casualties on exposed crew members even when armor penetration was unlikely. When weather conditions improved later in December and into January, Allied air power returned with devastating effect. Concentrated German armored formations moving along roads and choke points became highly vulnerable to air attack, further accelerating the collapse of the offensive. The Battle of the Bulge ultimately ended in failure for Germany. Hundreds of tanks were lost, along with experienced crews that could not be replaced. The offensive failed to achieve its strategic objectives, and by early 1945 the balance of the war had shifted decisively and irreversibly. Allied forces in the West prepared for the crossing of the Rhine, while Soviet armies advanced relentlessly from the east. Having shattered German defensive lines in massive winter offensives, Germany's industrial system was unraveling under the cumulative strain of strategic bombing, territorial losses, and the depletion of critical raw materials. Fuel shortages became catastrophic, and tungsten supplies dwindled further. Although Panther production reached approximately 3,900 vehicles in 1944, output declined sharply in the early months of 1945 as factories were damaged, transportation networks disrupted, and essential materials became unavailable. Even when new tanks left the assembly line, many never reached combat. Fuel shortages frequently rendered them immobile, forcing German units to abandon vehicles intact. In the war's final phase, tanks were often lost not to enemy fire, but to the inability to operate them at all. For the sake of historical balance, it is important to acknowledge the limitations of HVAP ammunition itself. The tungsten carbide core that gave these rounds their impressive penetration also introduced vulnerabilities. The material was extremely hard but brittle. If impact velocity dropped below a critical threshold, roughly between 2,300 and 2,500 feet per second, the core could fracture upon impact rather than penetrate armor. Under such conditions, the theoretical advantages of HVAP were significantly reduced. Nevertheless, within its constraints, HVAP ammunition represented a meaningful adaptation to the realities of late-war armored combat. It did not win the war on its own, but it contributed to restoring confidence, preserving initiative, and narrowing the gap between American and German armored capabilities at a critical moment in the conflict. As combat testing and battlefield experience accumulated, it became clear that the performance of HVAP ammunition was tightly linked to velocity. As range increased and projectile speed dropped, its effectiveness declined sharply. Against the Panther tank's gun mantlet, practical effectiveness was limited to roughly 1,000 meters. Beyond that distance, the likelihood that the tungsten core would fracture or disintegrate upon impact rose dramatically, reducing penetration reliability. American tank crews did not learn these constraints from manuals or classroom instruction. Instead, they often discovered them the hard way, under live fire. When HVAP rounds were fired at Panthers from beyond their optimal engagement distance, the results were frequently disappointing. Precious tungsten ammunition was expended without effect, while German tanks whose guns remained lethal at far greater ranges were able to return accurate fire. Compounding the problem was the rushed introduction of HVAP to frontline units. Ammunition shipments reached combat formations faster than training programs or technical documentation could be prepared. As a result, many crews developed their understanding of HVAP usage through direct combat experience, relying on improvisation, observation, and costly trial and error. One well-documented encounter illustrates both the promise and the hard limits of HVAP in real battlefield conditions. On November 20, 1944, Sergeant Francis Baker commanded a Sherman tank armed with a 76mm gun and supplied with HVAP rounds. His crew engaged a German Panther at an estimated distance of approximately 800 yards. During the engagement, Baker's gunner fired no fewer than 7 HVAP rounds, scoring multiple visible hits on the Panther's side armor. Despite these apparent successes, none of the shots achieved penetration. To Baker's frustration, the rounds deflected harmlessly from the armor plating. The incident highlighted a critical reality. Even HVAP struggled against sloped armor when impacts occurred at unfavorable angles. Although the Panther ultimately disengaged and withdrew, sparing Baker's crew further danger, the encounter served as a sobering lesson. HVAP was a valuable tool, but it was not a miracle weapon. Victories still depended on sound tactics, precise range judgment, intelligent target selection, and exploiting favorable angles whenever possible. HVAP improved the odds for American tankers, but only when combined with skill and disciplined decision-making. Post-war technical evaluations confirmed what frontline crews had already sensed through experience. When HVAP struck the Panther's gun mantlet within ranges of roughly 1 kilometer, its performance was impressive. Successful hits reliably pierced the armor and frequently caused catastrophic internal damage, including ammunition detonations and structural failure. Results were far less encouraging when HVAP was used against the Panther's glacis plate. Except at extremely close distances and under ideal impact angles, penetration was unlikely. The sharply sloped frontal armor caused many tungsten-cored projectiles to ricochet or shatter on contact, despite their high velocity. This reinforced the tactical truth that Sherman crews already understood: maneuver was essential. Flanking attacks, coordinated movement, and combined arms support remained necessary to defeat Panthers consistently. HVAP narrowed the gap between the Sherman and its German adversary, but it did not eliminate the technological disparity. What it offered was something previously lacking: a realistic chance in engagements that had once been nearly hopeless from the front. The outbreak of the Korean War in June 1950 provided another opportunity to assess HVAP under combat conditions. By this time, American Sherman tanks, primarily the M4A38 variant equipped with 76mm guns, faced Soviet-designed T-34-85 tanks operated by North Korean and later Chinese forces. The strategic context was very different from that of Europe in 1944. Tungsten supplies were no longer under extreme wartime pressure, and HVAP ammunition was available in substantial quantities. In Korea, American tank crews quickly found that HVAP rounds had little difficulty defeating the armor of the T-34-85 at typical combat ranges. While the T-34-85 was a capable and respected design, its armor protection was markedly inferior to that of the Panther. Its turret front, approximately 90mm thick, and its 45mm plate were unable to withstand high-velocity tungsten projectiles fired from American 76mm guns. As a result, Sherman units in Korea achieved strikingly favorable kill ratios against opposing armored forces. Superior training and crew coordination played a major role, but the widespread availability of HVAP ammunition was also a decisive factor. The 76mm Sherman, often criticized for its limitations in Europe, proved highly effective when paired with adequate ammunition supplies. For veterans of the European theater, this success carried a sense of irony. The very ammunition that could have altered many engagements against German armor had been too scarce to employ freely in 1944 and 1945. In Korea, freed from those logistical constraints, HVAP demonstrated its full destructive potential. German assessments conducted after the war further validated the significance of American HVAP development. Interrogations of captured personnel and reviews of German technical documents revealed a mixture of professional respect and lingering frustration. German ordnance specialists acknowledged that American industry had managed to solve the challenges of tungsten-cored ammunition production more effectively than Germany itself. This admission was particularly striking given that German engineers had pioneered much of the underlying technology. Although Germany fielded its own tungsten-cored rounds, such as the Panzer Granit 40 series, severe production limitations prevented these munitions from being issued in meaningful numbers. By late 1944, even with American access to tungsten still restricted, U.S. HVAP output far surpassed German capabilities. German tank crews interviewed after the conflict frequently cited improvements in American ammunition as a factor that complicated their battlefield assumptions. The realization that Sherman tanks could penetrate Panther mantlets at realistic combat distances undermined reliance on frontal armor as a shield. German commanders were forced to adopt more cautious movement, slower advances, and an increased dependence on defensive positioning. Ironically, this defensive posture surrendered initiative to American forces. It allowed U.S. units to integrate artillery, infantry, air support, and maneuver more effectively, eroding the advantages that German armor once held. The psychological impact of diminished armor and vulnerability played a significant role in shaping the increasingly reactive and defensive character of German armored operations during the final months of the war. In the end, HVAP did not overturn the balance of armored warfare on its own, but it reshaped expectations, altered tactics, and quietly marked the moment when American tank crews began to close a gap that had once seemed insurmountable. The forensic examination of high-velocity armor-piercing HVAP rounds recovered from destroyed German armored vehicles gave Axis engineers an unusually clear window into American ammunition engineering. What they found was not a revolutionary scientific breakthrough, but an exceptionally clever application of materials science under wartime constraints. At the heart of the American design was a dense tungsten carbide penetrator encased within a lightweight aluminum carrier. This configuration achieved a delicate balance. It concentrated mass exactly where it mattered while reducing overall projectile weight. The result was a round that maximized armor penetration while using remarkably small amounts of tungsten, an element that was scarce, expensive, and strategically vital. The lighter outer body allowed the projectile to achieve significantly higher muzzle velocities without imposing excessive stress or accelerated wear on gun barrels. Once fired, the tungsten core retained its kinetic energy far more effectively over distance than traditional steel penetrators, preserving lethality at ranges where conventional rounds lost effectiveness. From an engineering perspective, it was an elegant solution to a complex problem. German specialists fully understood the advantages of this approach. Their own research establishments were more than capable of appreciating the ballistic benefits involved. What they lacked was not knowledge, but the industrial and logistical foundation necessary to respond. By late 1944, Germany's armaments industry was operating under extreme pressure. Constant Allied air attacks, chronic material shortages, and collapsing transportation networks left little room for innovation. At that stage of the war, German tank and ammunition production was focused almost entirely on sustaining output of existing weapons rather than introducing new types. Factories were barely able to keep current assembly lines functioning, let alone retool them for experimental ammunition that required large quantities of tungsten Germany could no longer afford to divert. As a result, frontline German tanks in the final year of the conflict continued to rely on ammunition designs introduced in 1942 and 1943. From the German perspective, this stagnation did not initially appear disastrous. The Panther's 75mm K-42 gun already demonstrated formidable penetration capabilities when firing standard armor-piercing rounds, sufficient to defeat most Allied tanks under typical combat conditions. Improving ammunition performance further was not seen as a decisive priority compared to keeping vehicles operational and crews supplied. Meanwhile, American ordnance development continued to evolve incrementally. Although HVAP rounds were never available in unlimited quantities, their gradual introduction narrowed the technical gap enough to influence battlefield dynamics in critical engagements. The Battle of Arauco illustrates this shift with unusual clarity. Its historical importance lies not merely in tactical outcomes, but in what it revealed about modern warfare. The fighting demonstrated that American armored doctrine emphasizing maneuver, coordination between arms, flexible command, and sustained logistical support could reliably overcome German methods that placed disproportionate faith in individual tank superiority. German planners in 1944 had reorganized their Panzer brigades around the technical strengths of the Panther, assuming that superior armor protection and firepower would offset limited training, poor reconnaissance, and inadequate infantry or artillery support. At Arauco, this assumption collapsed. Panthers found themselves outmaneuvered, isolated, and destroyed not because they were inferior machines but because they were employed within a flawed operational framework. Observers on both sides drew the same conclusion. Superior engineering mattered and could provide real advantages. But battlefield success depended far more on combined arms integration, logistics, crew proficiency, and command flexibility than on raw technical specifications alone. HVAP ammunition also had a profound effect at the human level, an aspect often overlooked in purely mechanical analysis. For American tank crews who had endured the harsh fighting in Normandy while facing Panthers armed with only standard ammunition, the arrival of HVAP carried enormous psychological weight. It did not transform Shermans into invincible weapons, nor did it remove the Panther threat. What it did provide was something equally important: the belief that penetration was possible under the right conditions. This confidence encouraged more assertive tactics, quicker decision-making, and greater willingness to engage. Morale improved alongside performance, reinforcing a positive feedback loop on the battlefield. The effect on German crews ran in the opposite direction. The realization that American tanks could now threaten frontal armor fundamentally altered their tactical mindset. Otto Karius, one of Germany's most accomplished tank commanders and a veteran of Tiger operations, later wrote extensively about how crew morale was tied to the perceived invulnerability of their armor. As long as crews believed themselves largely immune to enemy fire, they fought aggressively and decisively. Once that perception eroded, behavior changed. Panther crews learned that the mantlet could be penetrated by HVAP under certain circumstances. That knowledge alone was enough to produce caution, hesitation, and slower engagement times. Tactical boldness diminished, and with it, overall effectiveness. At the strategic level, the development and deployment of HVAP ammunition underscores a broader truth about technological competition in modern war. Both the United States and Germany possessed capable engineers, advanced theoretical understanding of ballistics, and early awareness of the potential of tungsten-cored ammunition. Both nations produced workable designs. The decisive difference lay not in scientific brilliance but in industrial scale and resource security. American factories could manufacture HVAP rounds in numbers sufficient to influence combat outcomes, even if supply remained limited. German industry, by contrast, struggled to produce enough rounds even for evaluation. This imbalance repeated itself across countless weapon systems. Germany often fielded weapons of remarkable sophistication, yet lacked the capacity to deploy them in numbers that could alter the strategic balance. The United States produced equipment that was sometimes less refined but consistently reliable, supported by a logistical system capable of sustaining massive output. The comparison between tanks illustrates this reality starkly. The MiG-4 Sherman was not, by most technical standards, the most advanced tank of the Second World War. Yes, American industry built approximately 49,000 of them. German factories, under vastly different conditions, produced just over 6,000 Panthers. This near 8-to-1 disparity, combined with steady improvements such as HVAP ammunition, gradually neutralized German technical advantages and proved decisive. The legacy of Aracourt extended well beyond the battlefield. Many of the officers who fought there carried the lessons of that campaign into the post-war world. Lieutenant Colonel Creighton Abrams, who commanded the 37th Tank Battalion with notable effectiveness during the battle, later rose to become Chief of Staff of the United States Army. His name would eventually be given to the Mon Abrams main battle tank, a fitting symbol of how wartime experience shaped future military doctrine. In the end, HVAP was not simply a better projectile. It was a case study in how technology, industry, psychology, and doctrine intersect to determine outcomes in modern warfare. Throughout his military career, Creighton Abrams carried forward lessons forged in the harsh realities of World War II. Combat taught him that success in armored warfare depended not on a single technological advantage, but on the careful integration of multiple factors: combined arms coordination, well-trained crews, and critically reliable access to effective ammunition. These insights later shaped both his leadership philosophy and the armored doctrine he helped refine in the post-war era. When the United States developed the Mon Abrams main battle tank decades later, those wartime lessons were consciously embedded into its design. The vehicle was equipped with a high-velocity 120mm smoothbore cannon capable of firing advanced ammunition types, including depleted uranium penetrators. Functionally, these modern rounds filled the same battlefield role that HVAP ammunition had played during World War II, maximizing penetration by concentrating immense kinetic energy into a dense, fast-moving projectile. German tank veterans arrived at similar conclusions, though from a very different wartime experience. Former Panther crewmen who survived the conflict and later entered the ranks of the West German Bundeswehr had witnessed firsthand the limits of technological excellence unsupported by industrial scale and logistical depth. Their experience demonstrated that even the most formidable armor and firepower could be rendered ineffective without sustained production, maintenance, and ammunition supply. As a result, West German armor doctrine during the Cold War placed heavy emphasis on crew quality and training, while openly acknowledging that NATO forces, particularly West Germany, could not compete with the Soviet Union in sheer numbers. Yet Bundeswehr planners, informed by combat memory, also highlighted the decisive importance of ammunition performance. The Leopard 1 and later the Leopard 2 reflected this philosophy. Rather than relying solely on thicker armor, these tanks employed highly refined ammunition designs based on the understanding that projectile effectiveness and crew proficiency could rival raw protection in determining battlefield outcomes. With Germany's unconditional surrender on May 8, 1945, the immediate battlefield demand for HVAP rounds against Panther tanks came to an end. In the aftermath, American ordnance specialists undertook systematic examinations of destroyed German vehicles across Europe. Their findings confirmed that HVAP rounds had achieved successful penetrations under specific conditions, while also exposing their limitations. Vehicles struck by HVAP typically showed armor breaches in the turret face or gun mantlet when hit at favorable angles. In contrast, the Panther's sharply sloped glacis plate proved largely impervious, resisting penetration in the vast majority of documented cases. These observations reinforced American tactical doctrine, which stressed maneuver warfare, specifically flanking attacks and engagement geometry over frontal assaults against heavily protected targets. Comprehensive post-war assessments reached a clear conclusion. Although HVAP ammunition significantly enhanced the Sherman's ability to confront heavier German tanks, it was never the sole or even primary factor behind Allied success. Victory rested on a broader foundation: overwhelming numerical strength, superior logistics, total air dominance, highly effective artillery, and a more adaptable operational doctrine. The evolution of American tank crews between mid-1944 and early 1945 illustrated how these elements converged. Crews arriving in Normandy often faced German armor with genuine anxiety, particularly when confronting Panthers and Tigers that seemed impervious to standard weapons. Months later, the same forces had been transformed by continuous combat experience, improved training programs, greater availability of 76mm Shermans, and increasing familiarity with specialized ammunition such as HVAP. This shift in mindset carried real tactical consequences. Crews who believed in their equipment fought more assertively, recognized opportunities faster, and accepted calculated risks that earlier might have seemed unthinkable. HVAP ammunition alone did not create this confidence, but its demonstrated effectiveness played a meaningful role in strengthening morale and sharpening battlefield performance. The influence of HVAP development extended far beyond the war itself. From 1945 onward, American armored doctrine consistently treated ammunition effectiveness as a core design requirement rather than a secondary consideration. Modern tank rounds employing depleted uranium or tungsten alloys are built on the same physical principles identified during the war. Extreme density, exceptional hardness, and maximum velocity to concentrate kinetic energy into the smallest possible impact area. This conceptual continuity links wartime HVAP rounds directly to today's armor-piercing fin-stabilized discarding sabot APFSDS ammunition. Although the engineering has evolved dramatically, the underlying logic remains unchanged. Similar conclusions were reached independently by Soviet and later Russian weapons designers whose ammunition programs followed parallel paths rooted in the same physics of penetration. In this sense, The global tank ammunition industry traces a significant portion of its technological lineage to the HVAP experience. It was during World War II that engineers first demonstrated beyond doubt that specialized ammunition could partially offset even substantial armor advantages. One symbolic moment captured this transformation. On September 19, 1944, Sherman crews under the command of First Lieutenant Merwin Menke engaged Panther tanks using HVAP rounds near Ericourt. The encounter marked a psychological turning point. German crews, long accustomed to relying on superior armor, discovered that American tanks could threaten them frontally under certain conditions. American crews, previously burdened by a sense of inferiority, gained confidence from knowing they possessed a tool capable of defeating the Panther when used correctly. This change in battlefield psychology reverberated through subsequent armored engagements in Europe. Even though HVAP ammunition was never supplied in quantities commanders desired, its presence was sufficient to alter behavior. American tankers increasingly shifted from cautious defenders into assertive attackers, willing to engage German armor directly when circumstances allowed. The crews who fired those early HVAP rounds, watching tungsten cores tear through armor once thought invulnerable, proved a lasting lesson. Industrial capacity, combined with applied material science and tactical adaptation, could overcome even daunting technical disadvantages. That lesson, paid for in lives and experience across Europe's battlefields, remains directly relevant to modern military planners confronting the challenges of contemporary armored warfare.